So this is joint work with a couple of people I'm going to introduce in a second. It's about, roughly speaking, heterogeneous materials, stochastic homogenization, but more of a numerical aspect, kind of a question of numerical analysis. We were asking here about bias. It's somewhat, well, it's also a statistical question, a bias in a numerical method, and kind of comparing two different ways of dealing with it. And so this is joint work with three people who at some point were in Leipzig. So Nicolas Closeau, former PhD student of Antoine Gloria and myself, who is now in Vienna in Neuburg with Jan Fischer. Marc Josien, who is with the CEA, DEA.
CO.
CEA.
Anyways, it's better than being at North Street. And Young Zhu, who's and there are a couple of numerical collaborators I will mention also. So it's about heterogeneous media, and the approach is in some sense like it's standard in stochastic homogenization, pretty general. You kind of try to kind of treat different physical phenomena at the same time, like conductivity or elasticity. The important thing is that there is kind of a tensor which describes the material and which relates fields to fluxes. So for instance, in conductivity, this tensor would be the inverse resistivity, which is conductivity, and which relates the electrical field, the negative gradient of the electric potential, to the electric current Q. Or in elasticity, it would be the tensor of the elastic moduli, which relates the kind of local deformation on the linearized level as described by the strain to the stress of the material. And heterogeneity means that this material coefficient, this tensor field, depends on the position in your sample, and that's the starting point. And in these assumptions, so in the case of elasticity, one has to be a bit more general, but to focus ideas, let's look at a situation where this tensor field, which depends on space, and which for simplicity we assume to be symmetric, is uniformly elliptic in the sense that the quadratic form is bounded from below by some constant lambda, which is positive, and without generality by 1. And the object, the mathematical object one's interested in, is the elliptic operator, which arises from that coefficient field. So you take a potential u, you consider its gradient. That's a vector field. You multiply it with the tensor field, you get again a vector field, and then you take the divergence, or to be more precise, the negative divergence, which formally is the transpose of the gradient, and you get a scalar field again. And that's the elliptic operator, which one's interested in. And homogenization means that one wants to associate, one wants to simulate the behavior, kind of heterogeneous medium in terms of this operator to a homogeneous medium, so a medium where A does not depend on position anymore. And you want to do it in terms of the solution operator, and you can only hope to do it on large scales. So let's say for right-hand sides, which live on scales which are large, compared to the characteristic scale of variation of the medium, which here I would always think of being equal to 1. And stochastic homogenization means that we want to kind of consider a situation where we actually don't know the medium in detail. We just know we have certain statistical information about the medium. So it's a lack of knowledge, but it's kind of only a partial lack of knowledge in the sense that we're given the statistics, but we just don't know which realization we're looking at. So in that sense, it's kind of known unknowns in the sense that we're given, or we're supposed to know the probability measure on the space of coefficient fields, but not the individual realization. So, and then under very general situations, it's known that homogenization takes place so that indeed your solution operator can be kind of associated to a constant coefficient solution operator. And so one standard situation, which is completely deterministic, is the one of periodic coefficients. Let's say one periodic coefficients, then it's a classical result that homogenization takes place. But now here we're interested in the case of random coefficients. So we're given a probability measure. I will also use the name of ensemble, which is more of a physics name. And I will use kind of this symbol to denote the expectation with respect to that probability measure. So we're given an ensemble, which can be fairly general, but has to satisfy two important conditions, namely stationarity and ergodicity. And so stationarity is a quintessential structural condition on the statistics. It essentially tells you that if you look at the medium here, and you look at the medium at some other place, you look at your kind of surroundings, they will look the same statistically. So that's stationarity. Or in a kind of more mathematical way, if you look at your random field, your random coefficient field, and you shift it by 10 meters to the left, you get a new random coefficient field. And now you want to impose that these two satisfy the same law. So it's a kind of homogeneity in terms of the statistics. And if you don't put in some kind of homogeneity like this, there's no chance that you will get that homogenization takes place. I mean, if you want to end up with something homogeneous, you have to put in such an assumption. And here it's kind of homogeneity in the statistical form. So that's a kind of a very important structural condition. And ergodicity is a related but completely qualitative condition, which says that you really have randomness. You have a kind of sufficient amount of randomness in the sense that if you restrict your coefficient field on two different disjoint domains, then these restrictions become more and more statistically independent as the distance between the domains increases. So there are many ways of expressing this, but that's perhaps the most intuitive way of expressing ergodicity. So kind of a minimal amount of genuine randomness. And Kozlov on the one hand and Papanikolaou and Baradan already a while ago have shown that under these two conditions, homogenization does happen. So that's kind of famous result from these two schools. And now in this talk and in this work, we're interested in certain numerical aspects of this. So, so the question is, I mean, knowing that qualitative homogenization takes place is of course very valuable. But now, if you want to use that in practice, you want to kind of infer the effective behavior from the ensemble you're given. So that's a practical question. And there are numerical methods around for that, and that's goes by the name of representative volume element and method. And what I want to do in this talk is I want to scrutinize, I want to analyze the errors in this method, the quality of this method. So that's the goal. So it's, I mean, just to contrast it to, I mean, homogenization is a big area. I mean, also in numerical analysis, it's a very popular area. And so there is this term of numerical homogenization, where people, especially in the German-speaking world, Petersheim, Schwab, are very active. But that's kind of a different philosophy in the sense that no matter what heterogeneous coefficient field you're given, you want to kind of set up kind of an efficient numerical method that doesn't necessarily require resolving the small scale for every right-hand side. And it's also different from the theoretical concept of representative volume element as introduced in the engineering literature, where it's actually more of a kind of also that plays the role of kind of the concept of theoretical. So here I'm going to really explain to you this numerical method, and then we're going to look at the error. So that's perhaps the most important slide, which explains this this representative volume element method. So suppose you're given kind of a periodic realization of your coefficient field, L periodic. L is some kind of large number, large compared to, let's say, the variations of your coefficient field. And then you give yourself one of the Cartesian coordinates. I will always denote them by I. So I runs from 1 to D. And you're asked to solve the following kind of elliptic PDE. Namely, you're asked to find a correction to the affine coordinate function. Therefore it's called a corrector. So you want to correct the affine coordinate in the ith direction in such a way that the resulting function is harmonic with respect to your heterogeneous coefficient field. So that's the corrector. People in stochastic analysis would also say that kind of these functions as I runs from 1 to D provide harmonic coordinates. And now here you can take benefit of the periodicity of the coefficient field by imposing that the corrector, of course not this function, but that the corrector is periodic. So I kind of try to draw a picture, and I will show you some numericals. Okay, so what's the benefit of having this? What's the benefit of having this object? If you, the benefit is that once you have this object, you get a good approximation to the effective, to the homogenized behavior. So why is that the case? That's what I'm trying to explain here. Remember that the purpose of the microscopic conductivity, let's think of conductivity, is to relate the field to the flux, the electrical field to the current. And clearly here the field is given by the gradient of this function. So gradient plus the unit vector, I mean the Cartesian unit vector in the ith direction, and the flux is given by A times that quantity. And now the homogenized coefficient should somehow relate the macroscopic flux to the macroscopic field. That's what you want your homogenized coefficient to do. And what's the macroscopic field and the macroscopic flux here? Well, the macroscopic field should be the cell average of the actual microscopic field, and due to periodicity of the corrector, the gradient has vanishing average, so you pick up just the unit vector in the ith direction. And the macroscopic flux is, well, same principle, the cell average of this quantity. So therefore, you expect that the following quantity, which I will call A bar, provides a good approximation to the homogenized behavior. So A bar is given, so the matrix A bar is given as follows. You define how it acts on the unit vector, and it's given by this macroscopic flux, so the cell average of the microscopic. I just put this on the blackboard, but I'm sure many people have seen that. So you solve this equation on the torus, and then you say A bar applied to AI is defined as the cell average of the corresponding. Okay, so that's the kind of the first part of the representative volume element. But now clearly it requires having this L periodic coefficient field. So the question is, how do you get that? That's a non-trivial task. So there is a naive strategy, which, however, is kind of quite often used in practice. So you draw a sample from your ensemble. So you have a sample of your coefficient field in infinite space. Then you cut it out. You cut out this large box of side length L, and you extend that one periodically. And then you're in business. So you have this kind of periodic coefficient field A sub L, and you consider its the RVE applied to that map. So that's one strategy. That's perhaps, let's call it the naive strategy. Then there is kind of, let's say, a more educated strategy, better strategy, which however is somewhat subtle if you think about it. So because it asks you to construct kind of stationary ensembles of L periodic coefficient fields, which are somehow related to the original ensemble, to the original probability measure, but they're concentrated, they're supported just on L periodic coefficient fields. And then you sample from this different ensemble. And you use the same numerical method. And in a certain sense, the main storyline of what I want to tell you is that there is huge difference between these two approaches. If you do this the right way, and I will explain to you how it should be done, if you construct these periodized ensembles in the right way, then your statistical error, to be more precise, the bias, so the systematic statistical error, is much smaller in this strategy than in this strategy. So in the naive strategy, your statistical error goes like 1 over the size of this part of this volume, and in case of the educated method, it goes like 1 over the volume. So that's in 3 space dimensions, that's the difference between 1 over L and 1 over L cubed. And as I will point out later, 1 over L in 3 space dimensions is really bad because the random error is 1 over L 3/2. So if you run this strategy, the bias will be larger than kind of the fluctuating error than the random error. Whereas if you run this strategy, it will be much smaller. So it's a significant difference in terms of scale. And that's what I want to explain. Here, by the way, you see, so I had a collaboration with Matti Schneider, who was in Karlsruhe, and who's an author on the theoretical paper, where we kind of calculated huge samples. So Matti Schneider is an expert of generating ensembles, of generating samples of ensembles of non-overlapping inclusions of arbitrary shape. So here is kind of a non-overlapping inclusion of rod-like rod-like shapes. And we or he compared the rate of convergence in the stably logarithmic plot on the level of the bias between naive and the educated strategy, and you do see kind of the beginning of the asymptotic regime we theoretically are improving. So this difficulty one runs into with the, let me still call it the naive period method, is well known, and it's in principle. So here again is the naive strategy. So you sample from your original ensemble, you restrict your coefficient field to the period, to your large volume element, to your periodic cell of artificial period L. You extend periodically, and then you solve these problems. And clearly, you're doing kind of, in a certain sense, you're committing a crime, because here's again this picture. If you cut it out and you extend it periodically, of course, you completely alter the shapes of the inclusions, for instance. So it's clearly something very intrusive. And if I would show you a picture, even if L is much larger than here, if I would show you a picture of this kind of medium AL, you would be immediately able to say where I have cut, right? So you've kind of destroyed stationarity, you've destroyed this key property of homogenization, which is statistical homogeneity. So it's clearly a crime. And and people were aware of this crime, and in a certain sense, in a more finite element context, it was Tom Howe who kind of developed or analyzed the first methods to overcome this, and he, by oversampling, in a certain sense, stay away when you do this averaging, stay away from the boundary. But then it turns out that this oversampling is somewhat, the benefit of this oversampling is somewhat subtle, because the kind of the boundary layer effect, so the kind of the detrimental effect of the boundary layer, this artificial boundary effects, they only decay algebraically towards the center of your cell, and that's something which is also known from periodic homogenization, that if you have kind of a bad rational relationship, you may have very slow decay of your boundary correctors. And in stochastic homogenization, there is a similar phenomenon. So the benefit of this oversampling seems to be somewhat limited, as pointed out by Luis and collaborators, but then there's recent work by Peter Vella, Jan Fischer, Claudia Reitle, and Marc Lucien, who completely characterize these boundary correctors and then show, well, that's not so bad after all. So that's still under investigation. To quantify the beneficial effect of oversampling. There is a much more intrusive way of removing the effect of the detrimental effect of these boundary layers by introducing a massive term, which kind of leads to, for instance, on the level of the Green's function, leads to kind of pretty rapid decay. But then you fuss with your equation. So engineers perhaps don't like to do that, because if you have a legacy code for your elliptic problem, you don't want to go into the code to introduce additional terms. But that certainly can be done. But then there is, you have to relate this additional length scale here to the L, and you have to optimize. That has to be analyzed. So there are ways of to remedy the naive strategy, but that's not what I'm going to talk about today. So before giving you the result, let me give you a little bit of kind of intuition by showing to you some numerical simulations of this RVE method. And I will do that in case of kind of an interesting and theoretically and non-trivial example, which we got Poissonian ensemble. So let's think of kind of points which are randomly placed with density 1. So for the experts, according to the Poisson point process, let's consider balls of radius 1/4 around these points. So you have some overlap, but not complete overlap. And let's look at the union of all these balls, and then we choose A to be the identity on the union and equal to lambda times the identity on the complement. So that's that would be the whole space ensemble. And now this one is very easy. You don't even think about it, how to periodize it, because the Poisson point process, the driving process here, lives, of course, also on the torus, lives on any space endowed with a measure. And so it's very obvious how to put this ensemble on the torus. One doesn't even think about how to construct this periodized ensemble. And here are some numerical simulations to give you an idea of the simplicity, the conceptual simplicity of this RVE method, random represented volume element method. So you give yourself a Euclidean coordinate direction, let's say the E1 direction, and then you solve this this elliptic problem. And what I'm showing you here are, in the first row, you see the level sets of the electric potential, and in the second row, you see the current. And as you would expect, in the good, well-conducting regions, the level sets of the electric field are pretty spaced, whereas in the less well-conducting regions, they're dense. And kind of a similar phenomenon you see here for the current. There is quite some current in the well-conducting region, but then it has somehow to tunnel through across this badly conducting region. And once you have this current, you just take the average of the current of this field over the periodic cell. That gives you rho vector, which is the first row of the matrix, and then you do it for the second coordinate direction. And of course, the answer which you get is a fluctuating answer, because for different realizations of your medium, you get different answers. That's the random error. And it's also clear that this random error decreases as you make the size of your represented volume element larger. And making the size larger is the same as rescaling the inclusion. So here, instead of giving a picture which is 20 times larger, I rescale the picture. And it's also not surprising that the fluctuations go down as you make this lateral size larger, because there is some kind of self-averaging happening. And but what we're interested in is kind of the bias. And so it's clear that there is a bias, because if you think about the periodized ensemble, so looking at the Poisson point process on the torus, and then you roll it out as a periodic process into R2, of course you realize that you've introduced spurious long-range correlations. So it's clear that this ensemble is not the original ensemble, and therefore it's clear that there is a bias. And so that means even if you look at the expectation at the ensemble average of this numerical method, you get something that's still an approximation. You know that it has this, that it's isotropic because of the octahedral symmetry of the method, but so everything is in this number here, but this number just converges slowly. It's not, doesn't give you right away the answer. And that's the bias. So how quickly does the expected value converge to the homogenized value? And then in general, the total error this method commits is the sum, or on the level of the squares, the sum of the squares of the random error, the fluctuating part, and the systematic error, the bias. And qualitative theory tells you that both errors go to zero, but the question Juan Goya and I were starting with more than 15 years ago, still here in Bonn, was what's the rate? And in case of this ensemble, which I've shown to you, the random rate is actually easy. It has been established for quite a while. So you have a scaling that the square of the random error goes to zero, like 1 over the volume. That's the central limit theorem scaling, because in some sense it's the scaling acts as if you were adding up independent random variables. And by now there are much more precise information on this. And but when it came to the systematic error, we were only able to treat that one in a very specific model of a discrete medium, of a network of resistors, if you want, of IID resistivities, in which case, again, the periodization is obvious in kind of this discrete IID case. But in that case, we were able to show that the random error is much smaller than the systematic error, because without taking the square, it goes like 1 over the volume. And so that was essentially the state. And also in numerical simulations with numerical analysts from Leipzig, Boris and Verena Koromsky, we saw clearly kind of these different scaling laws in 2 and 3 dimensions, whereas kind of getting the bias is seeing experimentally the bias is numerically much more demanding, because you have to take these ensemble. I mean, you have to sample really a lot of samples to see the scaling of the expected value. Okay, so that was in a sense the state before we started asking the question, re-asking the question again about the bias. How much time do I still have?
You have 20 minutes.
Okay, so now what I showed to you are kind of numerical experiments and some theoretical results in case of 2 ensembles where it was very obvious how to periodize the ensemble. The first case was this Poissonian ensemble, which was driven by the Poisson point process. And since the Poisson point process is defined on the torus as well as in RD, periodization of that ensemble is obvious. The other case was the case of a discrete transistor and resistor network, in which case where we assumed that the resistivities were kind of independent from and identically distributed, independent from edge to edge. And also in this case, periodization of the ensemble is obvious because it's independent. It has kind of zero correlation length, if you want. And but what was not so clear is how to do it in a more general setting. And what turns out to be the right philosophy is to periodize the ensemble by conditioning on the realization being periodic. So what we advocate is the following way of periodizing the ensemble, namely just conditioning on the fact that your answer is periodic. So that's easily said in words, to condition on periodicity, but in practice, this is an extremely singular conditioning because in a sense, the set of periodic vector fields is very thin in the set of all vector fields. So it's an extremely singular conditioning, and as such, it doesn't really make sense. But just in the two examples which I explained before, the Poissonian ensemble and the discrete ensemble, that's exactly what we're doing, but there we're not even thinking about it because it's so obvious. So now the kind of from an applied math point of view, the task was to find a class of ensembles where this idea could be made rigorous. So where the saying let's condition on periodicity can be actually carried out. And that is the case when the underlying, that turns out to be easy, when the underlying noise is Gaussian, is a stationary Gaussian. So what we're given the data, I mean, one of the two building blocks of our ensemble is an underlying Gaussian field, which is stationary, so translation invariance, and let's say without loss of generality centered, so that it's completely determined by this covariance function or kernel, or rather by its Fourier transform, which is always non-negative as the basic property of the covariance function. And so conditioning on periodicity is nothing else than restricting the Fourier transform, which lives on the continuum dual space of all wave vectors Q, to the dual lattice, to the reciprocal lattice, which scales with 1 over L. So restricting the Fourier transform of the correlation function to the dual lattice is exactly the same thing as periodizing the correlation function like this, and is exactly the same thing as conditioning on periodicity. So here is a framework where this conditioning, which a priori would be kind of extremely singular, can be carried out in a rigorous way. And then, of course, a Gaussian field can never be uniform elliptic. So the second datum is a nonlinear transform. Let's say, think of the exponential if you want, which converts a Gaussian field into something that's positive definite. That's the class of ensembles we're working with. It's still fairly general, but it's clearly not kind of general theory. And here are kind of, again, in a more technical sense, the assumptions we make on the covariance function. It has to have some decay, integrable decay, and on the nonlinear A, which kind of converts a Gaussian field into a uniform elliptic field, which has to be at least twice differentiable. So those are the technical assumptions. And under these technical assumptions, we can prove that the systematic error is of the order L minus D. So reproving the result, getting rid of the logarithms we had before, and reproving the result we had before. But I think what's more interesting than this bare result is that we also get a representation of the leading order error, and that's this form of the result. So again, we're working again in kind of a class of ensembles, underlying Gaussian ensembles, as characterized by the covariance function and as characterized by this nonlinearity, which does have the obvious periodization. And what we show is that to leading order, the error can be represented can be factorized. And so the interesting result here is that the leading order error can be factorized into a part which just depends on the homogenized limit and the lattice, which here is a cubic lattice. But of course, if you think of kind of solid state physics, there is no reason for taking a cubic lattice instead of any other kind of hexagonal or BBC FCC lattice for your homogenization problem. So was just here for compliance that we took in the cubic lattice. So there's one factor which depends just on the homogenized limit and the lattice, and there is a second factor which is independent of the lattice and just depends on the limiting ensemble, on the whole space ensemble. So that's a kind of factorization result. And the first factor I could describe to you in pretty geometric terms. But in fact, what we really prove is we prove a finer statement where we don't look at the bias, but we look at the L derivative of the bias, and then we integrate in L, and that's the same right-hand side as before. And the first factor, in a certain sense, can be understood as looking at the non-singular part of the periodized Green's function of your lattice and how it depends on shearing or distorting the lattice. So that's what this tensor describes. The second tensor, that one is still a bit mysterious to us. So here it is. It's kind of some type of covariance function which depends on the corrector and even the second order corrector. And but we don't have a good interpretation of it. And this reminds me a little bit of the situation which was perhaps 5-6 years ago when Jean-Christophe Morat and I kind of identified the leading order variance of the corrector, but there wasn't a good interpretation of it. And then together with Armstrong, Jean-Christophe developed kind of a certain kind of universal understanding of this leading order random. And so that's something we're still lacking here, the interpretation of this blue part. But we can show that to leading order it's non-trivial, and it's even non-trivial in kind of the simplest situation when we think of an isotropic medium. There is kind of both factors have the right symmetry properties under isometry. So we found it after a while pretty useful to think in terms of this differential geometry language on how these tensors transform under transformation, covariant, contravariant, and so on, and that kind of clarified how they behave in the isotropic case, and we can show that for generic covariance function, indeed, this leading order does not vanish. Whereas if you do it in the naive way, and even if you do it not by periodizing but by reflection, so using Neumann instead of periodic boundary conditions, even if you do it just in one space, in one of the d directions, you get an error that scales like L-1, or the derivative scales like L-2. So there is this, rigorously, there is this huge difference between doing it naively and not, and doing it by periodizing the ensemble. So how much time do I spend?
10 minutes.
Okay, so let me just tell you one or two ingredients of the proof. So this is a statistical statement, right? I mean, it's about the bias. And so not surprisingly, there is one statistical ingredient we use. And in kind of, although it doesn't seem to be a very common name, we found it under the name of price formula. And price formula is tells you how the expectation of a random variable with respect to Gaussian ensemble changes as you change the Gaussian. And of this, we needed kind of an infinite dimensional version, which turns out to be pretty, in a certain sense, even clearer than the finite dimensional one, which was written down. And so there is a bit of functional analysis in the paper, in the sense that we have what's typically the case when you deal with Gaussian measures in infinite dimensions. We have a kind of a Hilbert space. We have a much larger Banach space in which this Gaussian measure, where the samples of the Gaussian measure live, whereas the covariance or the Cameron-Martin norm lives here. So we have this type of Gelfand triple for these three objects. And now we're given not just a single Gaussian, but we're given kind of a one parameter family of Gaussians parameterized by a parameter we call L, because that's what we have in mind, but it could be any parameter. And we make the assumption that the parameter derivative of the covariance function is uniformly bounded in this Hilbertian sense. And then we give ourselves a random variable, and the random variable is nothing else than a functional on this space, on this larger space, where kind of the samples live. And if this covariance function, if this random variable is twice differentiable, then there is this kind of very compact formula where the derivative of the expectation with respect to this parameter can be expressed as the expectation of the natural contraction of the Hessian, which is a bilinear form on X, and the derivative of the covariance function, which is bilinear form of U of X. And because of that, this contraction doesn't even require an additional kind of metric structure. It's really all the structure you need is on this side, and that's in a certain sense the key part of deriving this formula. And then in our case, these random variables are defined via PDE and derived, looking at their derivative, which in a certain sense means a Maillard type derivative, brings up Green's functions. We have to understand Green's functions. We get integrals which are not summable, and in order to make them summable, we have to we have to go to second order in homogenization. Only then these terms become summable, and therefore we need to use second order homogenization and quite a bit of kind of machinery on kind of how to approximate the quantity Green's function by the homogenized Green's function to second order. Okay, so but that's more technical. So I think there's also an interesting analysis there in terms of approximation of Green's function. But here this is more of an applied talk. So again, the main summary is the following. So we wanted to understand this representative volume element method, which is kind of the current method in the engineering literature, I would say. And we want to kind of compare these two strategies, the naive strategy being the one of periodizing the realization, and the kind of more educated strategy is the one of periodizing the ensemble. And the outcome is that at least in all the situations we know where this can be given a sense, so where it makes where you can make sense of the ensemble condition on being periodic, this gives you a much better answer in terms of bias than the naive strategy. And again, since the random error goes like L minus D over 2, this makes the difference. So the random error by the CLT scaling goes like L minus D over 2. And so in the naive strategy, the bias is larger than the random error. So that means you really have to do something about bias. Whereas if you periodize the ensemble, the bias is much smaller than the random error. So therefore, it makes really a kind of fundamental difference of what you do. Okay, so that's different.